Hello everyone, and thank you for your time today. Today's webinar will focus on best practices for the characterization of organic reactions using real-time in situ FTIR. During today's presentation, we will talk about getting started with data analysis. Then we'll go through the layout of the ICIR software and linked views. For today's presentation, I will be using the ICIR software version 4.0. We'll then go through some basic data analysis functions such as peak profiling, subtraction, and a brief introduction to ConcIRT. We'll then finish with your questions and hopefully some answers. In getting started with data analysis, one of the most important things is to understand and know the reaction chemistry scheme. So you want to have a good idea if we're looking for any intermediates, if mechanism is important, if just the endpoint is important for the project. Because we're utilizing the mid-infrared, we're going to be able to monitor the making and breaking of those chemical bonds. So we're going to be able to give a lot of information on the experiment. It's also good to understand the reaction workflow. And what I mean by that is what temperature changes are going to take place, what additions are going to take place over what time frame, or will they be a manual addition. And it's also good, which I'm sure you learned in the previous webinar, we highly recommend that you annotate these additions, these temperature changes, as well as any problems. And what I mean by problems is, did the stir stop? Was there a problem with a manual addition? So any type of perturbations to the experiment we'd really like to have annotated, because we want to be able to relate whether we're following a true chemical change or whether it's a physical change that happened within the experiment. Good quality data is very important. Again, as you learned from the previous webinar, we would love to start with good high signal to noise data and data that is free of water vapor. It's also a good idea to have reference spectra. We'd like to have reference spectra of components that you're interested in, that we might want to be able to follow. These can be from a spectral library, and by spectral library I do mean the spectral library from the ICIR software, not from a spectral library such as Aldrich. We do want you to collect spectra with your probe and your system as close to reaction conditions as possible. We can also get these reference spectra from the reaction data itself, and that's one of the things we will go through in this presentation. Here we have the acetic anhydride reaction from the ICIR software. And this is just the way that the software will come up from a reaction. And we have 4 tabs as well as our toolbox. Over to the right is our toolbox with the data treatments tab open. We have 4 views. This is the trend viewer where we'll be able to monitor our peak profiles as well as our ConcIRT profiles. The event viewer, which will show us where samples have been collected and will show us any annotations that we've made. Our surface viewer for our 3D reaction spectra. And the spectral viewer, which will allow us to overlay different samples or spectra at different points throughout the reaction. Now, what we mean by linked views is that if I select a point in the event viewer where we've made an addition, it will put a cursor in the trend viewer to show where that addition has occurred. It will show me the spectrum in the spectral viewer, and note that this spectrum will be gray in color, and it will also highlight that particular spectrum in the 3D viewer. So if we see a specific change in a trend that we're interested in, if we just put our cursor on that particular point in time, it will show us over in the event viewer if something has transpired and we've annotated at that point. And it will also show us the spectrum at that point in time, which we can again relate back to our chemistry. Moving forward to the data analysis functions that we're going to cover. The first will be pinning spectra. We will then go through how to create reference spectra from a data set. We'll go through peak profiling. We'll go through subtraction, baseline offset, and a brief introduction to ConcIRT. So again, getting started with the software, if we open up an experiment and one where we've just simply collected the data, we've not done any analysis in real time, this is what will be seen in the software. So here we don't have any trends. We have the last spectrum of the reaction in gray shown in the spectral viewer. Now, if we want to select spectra from throughout that reaction, there are 3 ways to do it. The first would be to go to your event viewer, and if you right-click on a sample, you will be given the opportunity to pin that spectrum. You can also, as you are just clicking through different samples, you can, in the spectral viewer, click on the button that looks like a push pin. And if we did have a trend open in the trend viewer, you could simply click on the push pin button in that view as well to pin the spectrum into the spectral viewer. And this will keep those spectra active and open in 2 dimensions in the spectral viewer as we're continuing on with our data analysis. So to review, right-click on a sample spectrum in the event viewer, or use the button, the push pin button in the spectral viewer or the trend viewer, are 3 different ways to where you can keep a spectrum active and open throughout your data analysis. Here is what I mean by pinning spectra. Here we have taken just several spectra throughout over the course of the reaction, and we have pinned them. And whenever we pin them, they change to they're given a color that's preset by the software. Now you can certainly change that color, but this just shows us starting with water, going to the addition of the acetic anhydride, and then the acetic acid forming. We can see the progression of the reaction here with our 2D spectra. Now it's important not to overlay too many spectra. When we're just starting with our data analysis, we just want to get an overview of how the spectra change throughout the reaction. So if we have too many, you'll begin to see what I like to call spaghetti on the screen, which is what you don't want. We want to be able to see what's changing in our data. Now that we've pinned some of our spectra, and I'm going to start here with the first spectrum of the reaction, which is water, I'd now like to create a reference spectrum of that water. Now, we talked about reference spectra, and of course we don't want to create work for ourselves. So if you know, according to your workflow, that the solvent is going to be the first thing in your reaction vessel, and that's going to be the only thing in there, you can collect it as your reference spectrum and not have to collect an outside spectrum of that solvent. So once we have pinned that spectrum, if you simply right mouse click on it, you're now given the option to create reference. Here you see in the next slide, we have the blue spectrum that we had selected, and now we have a green spectrum that says reference, and it gives us the time that spectrum was collected in the reaction. Now, of course, that doesn't mean a whole lot to us, so what we would like to do is rename it, of course, as our solvent. So if you right-click on that name, it will give you the option to rename the spectrum, and then we can type in water, so that we now have a reference spectrum of water from our data set. One of the most important things you will do in data analysis is profile peaks. So these are peaks that are changing throughout the reaction that can give you insight into how the reaction is progressing. So we can be following peaks that are going away, we can be following peaks that are coming in. It's very simple to profile a peak. all you have to do is double click on a peak of interest. Whenever you double click on that peak of interest, you will see a light orange band be shown on that peak, as well as the peak tab open up at the bottom of the spectral viewer window. Now, the software defaults to naming your peak just peak 1, 2, or 3, and it will also default to height to 0. What that means is we're going to profile that peak position to 0 absorbance. And for just an idea of how things are changing over time, height to 0 is perfectly fine, as is evidenced by the profile we see here. So in the bottom part of the slide here, we see our spectra. We see our peak with the little orange bar over it, that is the peak that we've profiled. And then in the trend viewer, we see how that peak changes over time. So this shows us that this is an anhydride peak that is going away. It's reacting away over time. Now, if you do want to change the type of peak, all you have to do is click on the Details button that's up next to the Pushpin button, and it will again give you your Peak Details tab at the bottom. And if we click on the type, it will then, on the drop-down list of the type, we can choose either height to single point baseline or height to 2-point baseline, in addition to the default height to 0. We recommend that you use height to single point baseline most of the time. So if I select that option, it will then give me a little red upside down triangle, which we can move to a baseline point. Now, it's important to choose a good baseline point, and a good baseline point is in the valley of your spectrum where really nothing else is absorbing. Now, this particular baseline point shows us that a lot of times we don't have a perfect option for a baseline point, so we just have to choose a good point in the valley where nothing else is absorbing. So here you can see the baseline point that I've chosen for this particular band. And the main reason that we're doing this is because, of course, this particular peak doesn't really go all the way to 0 absorbance. Here in the next slide, you can see the differences between the two types of peak profiles. In peak to 0 in green, with peak to baseline point in blue. Now you can see that the profiles are almost identical. It's just that the peak to baseline point gives a more accurate reflection of the absorbance value than does the peak to 0. But they are both identical in the way that they change over time. Another type of peak profiling is area. Now, the main reason we don't use area as much as we do height is simply because the reaction is dynamic, and we may have of course we have a lot of peaks that are changing, and you don't really want to be influencing one band by something that may be growing underneath it. But one area where area is important is if you are trying to profile a band that is growing off another band, which we have here. We have our water band at 1640, and then we have a very nice acid carbonyl for the acetic acid product growing off that water band. So what I want to do is use area to 2-point baseline and do what we call skim off the side of a peak to be able to follow that acid product. So again, I've just gone to the drop-down menu for type, and I've chosen area to 2-point baseline. Of course, in the group, I had to go and choose area. And then for this particular instance, we do recommend the peak start and stop and the baseline start and stop to be the same. That may not always be the case, but is a very good starting point. Here you see the profile of the acid and the area block down in the bottom in that light orange block over the spectra. And you can see up in our trend viewer the nice acid profile and how it follows with the anhydride going away. Moving on to subtraction. For this particular reaction, we might want to look at subtracting the water solvent. To do that, we go over to our toolbox and to the Data Treatments pane. The first option under the Data Treatments pane is our reference spectra, and then it says Subtract Spectrum, which is all highlighted here in the light red oval. If we select the drop-down list from the Subtract Spectrum, you can see that water, which we created earlier on as our reference spectrum, is one of our options. So if I then select water, you can now see that water is automatically subtracted from each spectrum in the experiment. You can see that where it says Subtract Spectrum, water is now listed. And if we look to our spectra themselves, you can see that the first two spectra are just flat lines because we have subtracted the water. You can also see that that 1640 water band is pretty much been subtracted from our spectra, and we can see the nice acid carbonyl, which we can now follow directly using a peak height profile in our trend viewer. Now, if we were not happy with these results, all we would have to do is go back to that drop-down list, select none, and then our data would be automatically put back to its original. The next data analysis function I'd like to go through is baseline offset. Baseline offset is very helpful if, like we've talked about before, we have temperature changes, especially if we have a heat up. Sometimes you will see your baseline increase as the reaction is heating up. And if that is causing us a problem in looking at some peaks of interest, baseline offset will allow us to correct for that fluctuation in baseline. So how do we do this? If we again go over to the Data Treatments pane and we go under Functions and you open the drop-down list, the first option is Baseline Offset. What I've highlighted here in this light red oval is the change in baseline that I would like to correct. And baseline offset will allow you to choose a point, a wave number position, and what it's going to do is bring the baseline point at that position to 0, which we can see here in the next slide. The baseline offset wave number position is 1888, and if we look over here to our red oval, you can see that at that point our baseline position is now at 0 at the wave number position of 1888. And it just makes those nice anhydride carbonyls a little bit more crisp, a little bit easier to see versus having the baseline fluctuate on us. So again, if you do have some peaks of interest and you do see a baseline fluctuation, I recommend that you try baseline offset. And again, if it doesn't work like you expected, you can always go back to the drop-down list and select none, and that will be immediately taken away from your data set. I'd now like to go through a brief introduction to ConcIRT. Now, ConcIRT is a proprietary algorithm of METTLER TOLEDO's which takes a given region of the spectrum and a given time frame of the reaction and deconvolutes this data into the components that are changing at different rates. So ConcIRT will give us both the relative concentration profiles and their corresponding component spectra whenever it is enabled. Now, to enable ConcIRT, we go over to the Data Treatments pane, and underneath the ConcIRT area, you can check the box Enable, and it will engage the ConcIRT algorithm. If you click the Show Components box, that will show you the corresponding component spectra. If you automatically engage ConcIRT, it will use the default region of 1900 to 900. Now in this case, for our acetic anhydride reaction, I'd like to choose my own spectral region. So if I click on the expansion box next to the spectral region, it allows me to choose the spectral region of interest for my reaction, which is what I have done here. The results are shown in the next slide, where I have shown or where ConcIRT has given us, and I have named the profiles: the solvent of the water, which is in pink, the anhydride reactant in turquoise, and the acetic anhydride product in purple. The acetic acid product in purple. So what we have here, you can see the profiles as well as their corresponding spectra in the spectral viewer below. And you can see what a nice job the ConcIRT algorithm does. If we look at the pink solvent spectrum and then that red spectrum, which is the first spectrum of the reaction, we can see it's just a very nice clean spectrum of water. If we look to the turquoise spectrum, the anhydride, and then the green spectrum, which is about 4 minutes into the reaction where we've added the anhydride, you can see how it pulls out the anhydride carbonyls and the subsequent bands in the fingerprint region of the spectrum for anhydride. And then if we look to the acetic acid product spectrum, you can certainly see the acid carbonyl. We see no water, and then you see the other acid bands throughout the fingerprint region of the spectrum. Now, we're not going to say that ConcIRT is going to work on everything, but it is a really, really good first start, and it can do a very wonderful job for you. Now, this is just a brief introduction to ConcIRT. The next webinar in this series will give you an in-depth look into the ConcIRT algorithm. So let's just go through some tips for successful data analysis. I highly encourage that you use the linked views and the process knowledge that you have to relate spectral changes to their chemical or the possible physical counterparts. It's very helpful. Annotations, I can't tell you how much we highly recommend annotations because it does make the data analysis so much more straightforward. Always start simple. Don't try and overlay too many spectra at once. Again, go back to your process knowledge and just overlay a spectrum at each large juncture in the reaction. After an addition, after a temperature change, but just don't overlay too many at once. Start simple, get a good idea of what's transpiring. Try ConcIRT. Let the software do the work for you. That's one of the first things that I do is just enable ConcIRT and let's see what it comes back with. A lot of times we can sit there and we can look at the data and ConcIRT can highlight things that we miss. It's a great way, and it can point out things that you may have missed, and you can say, wow, there's a peak of interest. Go back and profile it, and there's your answer. It can bring out interactions. It can show you intermediates. It can really help you elucidate mechanisms. If you're looking at a profile and it's really not making sense according to your chemistry, go back and look at the peak that you're profiling and any baseline points that you may be using, because a lot of times, again, you could have an intermediate that's growing in and out on you. So if the profile doesn't make sense, of course we're all human. Don't discount human error in looking at those positions. And as I just pointed out, ConcIRT can profile interactions between species, and it can be very helpful in elucidating mechanistic information, as well as any possible physical interactions. What I mean by physical interactions, one good example is viscosity. Sometimes ConcIRT can show you viscosity. It can show you temperature. It can pull out a lot of different things. So it is a very, very useful tool. So I hope this webinar has given you a good introduction to data analysis. And now I'd be happy to take any questions that you might have. And again, thank you for your time today.